Hi, everyone. Thank you for joining us for our webinar with Emerson titled Achieving Measurement Confidence, the Power of Enhanced Coriolis Diagnostics. I'm Robin Tucker, Editor-in-Chief of Flow Control. First, let's take care of a little housekeeping before our presentation. If you have questions or any technical problems during the presentation, please type them in the question box. We will take care of any technology issues as they occur, and we will answer your questions about the presentation at the end of the webinar. If we don't get to all of the questions, we'll post the responses on flowcontrolnetwork.com as soon as possible. Our speakers today are Taylor Scott and Tom O'Banion. Taylor is Product Marketing Manager for Emerson's Coriolis software products, including Smart Meter Verification, Advanced Phase Measurement, Concentration Measurement, Batching Control, Net Oil Calculator, among others. Tom is the Director of Global Chemical Application Innovation for Emerson Automation Solutions, Micromotion. He has 30 years of industrial application experience in a variety of roles, including greenhouse gas compliance, process and natural gas market development, and technical sales management covering Canada, Taiwan, and mainland China. Taylor and Tom, I now turn it over to you for more details.
All right. Thank you, Robin, for the introduction and for hosting the webinar. Thank you to everyone who's joining, potentially over your lunch hour. Appreciate you being here for our webinar, where we'll be talking about how to achieve measurement confidence with the power of enhanced Coriolis diagnostics. So today we're going to walk through why instrumentation diagnostics are important now more than ever, what sort of recent advancements have been made to Coriolis diagnostics, as well as some examples about how they're making people's lives easier by improving operational certainty and effectiveness. So, like Robin said, some introductions. My name is Taylor Scott. I manage the Coriolis software portfolio over here at Emerson Micromotion, and I'll be co-presenting today with Tom O'Banion, who leads innovations in new product development with an emphasis on applications in the chemical industry. So why are we here today? For those that can't see it, we have one process engineer telling the other, and that, in simple terms, is my idea on how to increase factory optimization. Any questions? Clearly, lots of questions, and I think a lot of us can relate to this sort of feeling. No matter what industry you're in, we live in a world that's becoming more complex every minute. More instruments, more data from those instruments, and more decisions that need to be made based upon those instruments. And automation can certainly augment some of the human expertise, but there's still this need to turn large amounts of data into useful information, because useful information leads to those better decisions. First, I want to start off with a quick question here, just to get a pulse for who's joining today so we can best tailor the webinar. What best describes your industry that you're representing? Go ahead and give everyone a couple minutes here. All right.
And here it comes in and Q&A.
All right. Lots of oil and gas representatives today, as well as chemical. Great to see everyone joining. I know we probably have some folks from other industries, but glad you all are here. And I think we'll have some great presentation for you. So back to those questions. Any questions? Yes, many. For instrumentation, here we go. For instrumentation, and specifically for Coriolis meters, we see some common themes in the sorts of questions that we get, especially related to diagnostics. Things like, even if the meter was recently calibrated, how can we be sure that it's accurate under current flowing conditions? That's a pretty important one. Is there any way to detect coating or buildup in the meter, and do those sorts of things affect my accuracy? Even if the meter isn't alarming, is there anything we can do to improve the performance? And a lot of times we get questions about, is there a way to prove to third parties that the meter doesn't need recalibration? Is there a way to extend our proving intervals if we know that the meter doesn't drift? And that's why we're here today. We're going to explore how Coriolis verification technology can help answer these questions, among others, without removing the meter from the line and without affecting the measurement, and ultimately in a way that can be integrated with host systems. So let's dive in and we'll walk through smart meter verification and how it turns data into useful information. First, we're going to start with a quick video just to make sure everyone's up to speed on how Coriolis meter works. So I recommend turning on the sound on your computer, and we'll go through this quick 2-minute video.
How does a micromotion Coriolis flow meter measure mass flow and density? The flow meter has dual parallel flow tubes. When the process fluid enters the sensor, it is split. Half of the fluid passes through each tube. During operation, a drive coil stimulates the tubes to oscillate in opposition to each other at the natural resonant frequency of the tubes. Magnet and coil assemblies, which are called pickoffs, are mounted on the flow tubes. As the tubes oscillate, the voltage generated from each pickoff creates a sine wave. The sine waves generated indicate the motion of one tube relative to the other. When there is no flow, the inlet and outlet sine waves are in phase, meaning they are in a synchronized motion. When fluid is moving through the sensor's tubes, Coriolis forces are induced in both flow tubes. These forces cause the flow tubes to twist in opposition to each other. As a result of the twist in the flow tubes, the sine waves are now shifted in phase with respect to each other and are asynchronous. The time delay between the two sine waves is measured in microseconds and is called delta t. Delta t is directly proportional to the mass flow rate. The greater the delta t created by the Coriolis force, the greater the mass flow rate. While the sine wave phase shift indicates mass flow, the wave frequency indicates density. When the liquid density changes, the vibrating frequency of the tubes also changes. Consider an example of a spring and weight system. A larger mass has a lower frequency of oscillation, while a smaller mass has a higher frequency. In the Coriolis sensor, the tubes correspond to the spring. The mass of the tubes and the fluid they contain correspond to the weight at the end of the spring. The stiffness of the flow tubes remains essentially constant. Therefore, the mass and density of the fluid contained in the fixed volume of the flow tubes is the only variable affecting the frequency. Liquid volume flow is derived from the mass flow and density measurements already acquired. As in this example, fluids can have the same volume, but different densities and masses. The mass and density measurements allow the calculation of the volume flow.
So Coriolis meters are multivariable devices, which means that they directly measure mass, density, and temperature. They don't have moving parts, and they don't require straight runs of pipe to be effective. And they can be very stable over a long period of time, as we see here in this example. What we're looking at here is about 12 years of proving data for 6 different Coriolis meters that were installed in a cavern storage application up in Alberta, Canada. Despite cat fines and other sort of particulates over 12 years, these meters have maintained very stable meter factors throughout their lifetime, as you can see. This is a really common story when it comes to Coriolis meters, and we'll revisit this application later in the webinar. They can be stable, but we live in an imperfect world, right? Moisture and improper installation can sometimes lead to electrical issues. Corrosion could be an issue if there's any unexpected changes in concentration or temperature. Buildup can occur, especially when paraffin is present in a wellhead, for example. And erosion can be an issue if there's some sort of abrasive slurry that's being dealt with. And even if the meter is healthy, there can sometimes be unexpected process upsets like multiphase flow that can have some sort of effect on Coriolis accuracy. And these challenges can impact different sorts of people. So an instrument tech, for example, they need to understand if the meter is properly maintained. Whereas the metrology manager might be looking for something that will make it easier to deal with the increasing amount of regulations. And at the same time, process engineers are always looking for ways to understand what's actually happening inside their pipelines and their tanks. So we can see there's a variety of reasons to verify our instruments. Keeping an audit trail of instrument performance over time is pretty important for something like ISO 9001 compliance, as well as a variety of external third parties. So for example, the EPA or API or the FDA, among others. And there's a lot of focus on big data these days, like we've already talked about. And while automation and data analytics programs can be powerful, they're really only as good as the data that we're feeding into them. So we need to make sure that we have high quality data and diagnostics that are coming out of our devices and getting them to the right decision makers. Which is why diagnostics that evaluate complete measurement performance are so important. So how can this be achieved in the context of Coriolis meters? First, calibration factors have a lot to do with mass flow and density accuracy. So we'll discuss how evaluating tube stiffness can be a very robust way to verify a Coriolis meter's calibration. But we shouldn't stop there. We also need to verify how the electronics and the outputs and if they're operating as designed. Keeping track of any sort of changes to configuration data or zeros, whether they're authorized or not, is also important for keeping a proper audit trail of our instruments. And like we've already discussed, we need to look beyond the meter to understand how multiphase flow, changing flow rates, coding and buildup can have an effect on measurement performance in some cases. Let's back up really quick before we dive in. What exactly does verification mean? Let's get clear on our terminology. So calibration is a very well-known concept in the instrumentation world. When we calibrate a Coriolis meter, we're establishing the relationship between the true flow rate through the meter and that vibrational delta T signal that's produced by the meter. This relationship defines the flow calibration factor, which is directly proportional and unique to each meter's tube stiffness. This relationship is typically defined in a traceable and accredited laboratory environment. Moving on, we have validations, and validations are sometimes used as a proxy for calibrations, especially in custody transfer applications in the field. So when we're comparing the performance of a meter in question to a reference meter, we're performing a validation. Now, verifications, which is what we're talking about today, are when we correlate diagnostics to the primary variables to tell us something about measurement performance. So for example, when we look for a change in tube stiffness as a diagnostic, as a way to evaluate the current calibration factors, we're performing a verification. And calibrations and validations certainly have their place, but especially in applications where Coriolis meters are known to be stable and not require recalibration, these external processes can result in some unnecessary downtime and in some cases even safety risks that come with breaking seals and removing meters from the line. Manual verifications is something that can be performed in lieu of calibrations and provings, but often they require a trained technician to be on site. And they can still require disconnecting the meter from a host system, and there's the potential for human error with these sorts of manual processes, although it can generally help you avoid removing the meter. Which is exactly why we're seeing these sort of in situ or inline verifications becoming more and more popular in the process industries today. In situ verifications don't stop at the laboratory door. They evaluate meters under as-installed conditions, which can be very powerful. The ability to have this sort of on-demand and automated verification that doesn't interrupt the measurement is quickly becoming the new standard for Coriolis Diagnostics. Which brings us to SMV, Smart Meter Verification, which is a suite of automated in situ diagnostics for Emerson's Coriolis meters. SMV Basic is something that's new, which verifies a meter's calibration and its electronics. It's now included as a standard feature. SMV Professional can be licensed to produce verification reports, and those are recognized by a lot of third parties, like we mentioned with the EPA, FDA, API, and even for SIS applications, among others. SMV Professional also includes diagnostics that go beyond the meter to evaluate total measurement performance. So let's dig into exactly how these diagnostics work, and then we'll walk through some real-world examples of how they've been used. At the factory, each Coriolis meter is calibrated, like we talked about, and it's calibrated with its own unique mass flow and density calibration factors. As you'll remember, calibration defines the relationship between true flow properties and the vibrational response of the meter. And because each meter has slightly unique metallurgical properties, each meter has a slightly unique calibration factor and a unique stiffness value. Therefore, if a change in tube stiffness is detected in the field, the meter will likely require a recalibration or perhaps even replacement. So how can we detect a change in stiffness? Well, we start by characterizing what's called the frequency response function, which you'll see on the right part of your screen. All vibrational systems have a unique frequency response function curve, which is what represents how it responds to a stimulus. The first thing most people notice about this curve is the peak, which represents the meter's natural frequency. Like we saw in the video there, the meter's drive coils stimulate the Coriolis tubes at this frequency because it's most efficient and maximizes the meter's signal-to-noise ratio. But how do we measure stiffness? Well, all frequency response function curves are defined by three values: mass, dampening, and stiffness. So if you remember back to your days of algebra class, in order to solve for an equation with three unknowns, we need at least three equations or three data points. So what we do, as you'll see on the 5 little dots on that frequency response function curve, is we drive the meter at 5 different frequencies. That helps us define the curve and solve for the meter's mass, dampening, and stiffness. So in order to verify a meter's calibration factors, we just verify that stiffness has not changed. And to do this, a meter's stiffness baseline is measured and stored at the factory where it's calibrated. Each meter, like we said, has a slightly unique baseline, so you could think of this baseline like a fingerprint. Then in the field, stiffness is measured and compared using the same method, and it's compared to the factory baseline. If the stiffness has not changed, the existing calibration factors are verified. If there has been any statistically significant change in stiffness, we're alerted that an inspection should be performed, which may result in the need to recalibrate or replace the meter. And it's important that a change in structural integrity of the tubes is detected before it becomes a safety issue in some cases. So here what we're looking at is some data from a chemical manufacturer's laboratory where they actually purposely corroded a meter to test SMV. In this experiment, SMV detected the corrosive damage about 2 weeks before the technician noticed the primary containment failure. This experiment shows the power of how diagnostics can have a tangible impact on reducing unintentional exposure to harmful fluids. Another way to think about this too is the concept of a bell, right? A bell has a certain tone when it's hit, and if the bell becomes damaged, it's going to ring with a different tone when it's hit again. The bell's tone will also change if any sort of buildup or gunk is stuck on the bell. And so improved methods for analyzing this tube integrity data now enables us to detect buildup or coating within the Coriolis tubes. Although coating and buildup typically doesn't damage the integrity of the tubes, it can affect accuracy in some situations. And this is especially prevalent in upstream oil and gas applications, especially when paraffin is present, or colder temperatures exist when paraffin is present. It's not uncommon for meters to fail approving because of buildup. So we're typically forced to either clean the meter before every single proof, even if it's not coated, or divert flow until a hot oil or a steam truck can arrive on site. With the ability to detect coating through diagnostics, though, we can clean the meter proactively and only when it's needed to avoid those failed provings. Another example where coating can be valuable is with expanding regulations in the food and beverage industry or even the chemical industry. The early detection of residue can lead to an improved confidence in the safety, quality, and the compliance of our products. Next, let's discuss how process diagnostics can build even more confidence in Coriolis measurement performance. Because Coriolis meters directly measure mass flow, they're very well known for their performance under mild multi-phase flow conditions, like entrained air or wet gas. But when unexpected and severe multi-phase flow conditions are present, especially in batching operations, where a pump may have been improperly started or maybe some valves were opened in the wrong order, measurement errors can lead to quality or even custody transfer challenges. So a live multi-phase flow diagnostic can empower us to avoid and even correct for some of these occasional operational oversights. Because multiple phases of a fluid tend to decouple under vibrating conditions, the severity of the entrained air or wet gas can actually be calculated directly by the Coriolis meter by monitoring how hard the meter is working to vibrate the tubes. Therefore, a Coriolis meter can alert us when moderate and severe multiphase flows are present. So while moderate multiphase flow typically doesn't affect measurement performance, it can be useful when diagnosing the root cause of a process upset. It can also be useful to know when severe multiphase flow is present, so the proper steps can be taken and we can remediate the potential for any measurement errors. While Coriolis meters are also known for their high rangeability and turn down, all instruments have limits, right? And dramatic changes in operations can occur. So for example, if a meter is originally sized for a well's peak flow rate, but the well begins to produce at a much lower rate, as they often do, a resizing or repurposing of the meter may be beneficial to maintain measurement performance on the well. On the other hand, some companies will periodically repurpose instruments or rotate their installation points. So how can we be sure the meters are performing as they should, regardless of these sort of operational changes? Well, new diagnostics can alert us to when to verify a meter zero because of high turn down or even large temperature shifts. These flow range diagnostics can also recommend increasing the flow rate through the meter in the unlikely event that it shifts beyond the meter's spec. These built-in diagnostics can free up engineers to worry about more pressing issues. While straight pipe runs, like we said, are not required for Coriolis meter performance, it's important to verify that any stress from misaligned pipes are not causing shifts in meter zero. So new diagnostics monitor the stability of the meter's live zero under no flow conditions, and we can compare that live zero to the factory zero. This allows us to detect the presence of any pipe stress so that we can take the steps to correct that pipe misalignment and avoid the potential for any sort of related measurement errors. We've covered a pretty large variety of meter and process diagnostics, but how can we realize their value within our existing operations? While all these diagnostics can be integrated through traditional communication protocols, things like Modbus, discrete outputs, etc., Emerson's ProLink software brings this together in a pretty intuitive interface that guides users to more quickly diagnose and fix any sort of issues. As you'll see here, the visual cues enable users to drill down pretty quickly to the relevant and active historical alert trends, as well as any possible changes to tube stiffness, zero, or configuration data, and as well as the current and historical process upsets. It can also be important to tie these diagnostics together in a way that can easily be stored and shared. The SMV report gives a high-level summary of meter and process health, as well as serial numbers and calibration data that you'd expect to see on a calibration report. Background information is also included to explain the test background methodology. And now I'm going to hand it over to Tom, and he's going to walk through some of the third-party testing that's been done with some of these diagnostics, as well as some really awesome real-world stories about how Coriolis diagnostics and reports are making people's lives easier.
Fantastic. Thanks so much, Taylor. We've got some real nice questions coming in, too, so I think that'll be a very enjoyable part of this. My job here the last few years has been focusing on third-party agency recognition of SMV, a wide variety of industries and different kind of regulatory bodies. And the whole goal of that really is to make your lives easier if you're governed by an API or Food and Drug Administration and they're willing to accept verification as part of your calibration or proving process. It can definitely save you money. One of the places that we started, because customers were really, really interested in third-party data, we've done a fair bit of testing internally, but we went outside. We used the Netherlands Measurement Institute conducted a study that ran right around $100,000. And the goal of that was to run SMV under real-world conditions. So we tested meters at NEL in Scotland on liquid. We sent meters to Pigsar in Germany for gas. And the whole goal of that was to show the robustness and the reliability of SMV under a very wide range of temperatures, pressure, flow, density, flow noise, and viscosity. The letter is a little hard to read here, but basically NMI says that if you pass smart meter verification, the meter is within the original factory specification, and it can be used as a reliable tool to confirm that the meter is measuring accurately. It can definitely be used to extend proving intervals and calibration frequencies depending on what agency you're working with. The first one, specific agency we'd like to talk about is the U.S. EPA for greenhouse gas. The legislation is 40 CFR Part 98, and basically it's a carbon measurement system where the EPA requires major producers of CO2 and other global warming potential gases to report their use or their emission to the government. The accuracy required in those devices is typically not as stringent as a Coriolis meter could offer, but one of the things that we discovered is using more traditional flow measurement technologies such as orifice plates. Those plates would have to be physically inspected and photo documented every few years. Now, you all know that most of the orifice plates in use in industry are bolted in line. You're not using senior orifice type fittings where the orifice plate can be removed while you're flowing. So from an operational point of view, compliance became a real sticky point for these users. We've put a few thousand meters in the service. We have a definitive letter and set of test data that shows that it's a very valid approach in lieu of wet calibration of these Coriolis meters. We have documented cases of up to $300,000 in capital and $300,000 of annual expense savings by the use of Coriolis and SMV. To our knowledge, we've survived passed handsomely every audit or every inspection by the EPA. So it's a safe diagnostic technique to use. Next, I'd like to talk about AGA number 11, which also got published as a joint standard by the API. It's chapter 14.9 of the NPMs. I'm actually one of the original authors of this in the late 90s. The revision that came out in 2013 actually has a section where meter verification is specified as an acceptable alternative to gas calibration. Gas calibrations are quite a bit more difficult than liquid. There's fewer labs. They're not as accurate. And so this was really quite a breakthrough. AGA is interesting in the fact that they also wanted the user to verify the RTD. And those of you measuring gas know gas applications tend to be lower in the flow range, so zero becomes more important. So they want the user to also check that. If you pass RTD, pass zero, and pass smart meter verification, you're essentially done. You put that in the file. You can leave that meter in service. You can run SMV while you're flowing. And as long as you pass SMV, you don't ever need to calibrate, according to AGA 11. The next one we're excited to talk about, and this was one of the questions submitted. Much like partial stroking of a valve, SMV offers a lot of value in safety instrumented systems by allowing you to extend the interval that a wet calibration might be required. We've got some very high scores from our FMEDA. Our legacy products are in the 93% safe failure fraction. The newer products are as high as 97. The proof test coverage, looking at dangerous undetected faults, using SMV and doing a 4 to 20 loop check plus a RTD check, is 91% coverage. The picture on the lower right is actually a major chemical producer out of Europe. They wrote a paper for Emerson Exchange documenting how much the proof test could be extended, and they said savings up to $5,000 per year per meter were experienced. And again, for safety, this is a great diagnostic because the meter stays in the line, the safety function continues to operate while you're verifying the meter. So this diagnostic actually enhances the safety of the safety function. Next one we'd like to talk about is in the food space. FDA, both the traditional 21 CFR Part 11 as well as the Food Safety Management Act requires checking of flow meters and verifying that they haven't shifted. Much like the EPA letter, we have authored a definitive letter by our VP of Quality that says you run SMV, we recommend quarterly, and that should be with proper record keeping that should be in full compliance with the FDA requirements. Next one that we're very excited about, this was just released last year and a half ago, is API NPMs Chapter 20.2 that covers allocation measurement. The predecessor to this had wording including that the operator should have a plan for proving or calibration. Those of you in the oil and gas space know that when API says that, should means it's up to you to evaluate kind of risk versus return. Many users had elected to only infrequently check those meters. Allocation standards are fairly loose. In the 1 to 2% range is what we hear a lot, maybe 2% for the whole system, 1% for the meter. When API released 20.2, they made a very significant change in that this standard describes the entire allocation measurement system, but changes the word should to shall. Shall carries the weight of law in effect. So allocation measurement customers are changing their procedures as we speak, and meter verification is recognized as a piece of that whole proving and verification practice. API didn't specify how frequently you need to check the meters and how many of the proving runs you might be able to eliminate. So we're actually working with several key clients right now to form best practices around that. A couple others we have in here. ISO 9001 is used a lot in food and beverage, pharmaceutical, life science. Fairly loose wording. It's 7.6 paragraph A that talks about the meter shall be calibrated or verified or both, traceable to national standards. We believe, based on the original ISO 17025 accredited calibration, along with smart meter verification, that we're in full compliance with this. It's very handy to incorporate that into your plants or mills work practice and documentation. Taylor showed just some of this data. This is a key customer, actually Kira Energy in Alberta. This is very exciting because they saw all these years of proving data and actually approached the government and said, this is very expensive and it's really not yielding us much value. So they pushed pretty hard and did a pilot program where they actually proved the meters and also ran SMV. They actually approached the government and said, we petition you to change the law. So in Alberta, Directive 17 has been written that states that meter verification can be used to replace some or potentially even all of the proving runs. Measurement Canada is interested in this, And we have a number of customers that have operations both in Canada as well as the U.S. that want us to leverage this and increase our efforts with API, which ultimately would be Chapter 5.6 for custody transfer. This is one I was very involved with over the last 3 years. We actually, as part of our overall approval to sell products in Russia, did a very extensive test here at the factory and developed a somewhat special SMV routine that allows us to be used in lieu of wet calibrations for basic metrology. So it doesn't include pure physical transfer, but it includes measurement down to the 0.25% accuracy range. And SMV is run once a quarter. Assuming that you pass all of those, you can extend the calibration interval. It used to be annually, and now it's once every 4 years. So big cost savings there. A few examples of meters that we've had returned here. The testing that we had done in Europe by NMI was on new meters and pretty clean fluid. So it was natural for customers to say, well, we hardly ever see a Coriolis meter damaged. You know, hopefully you guys see a few that you can document. So we put several case studies in here to share with you and show that SMV actually does detect meter damage. This meter was on an acidic slurry in the oil patch in Alberta. We don't know exactly what happened. The meter came to us because the mass balance wasn't working by the customer. They had unfortunately not run SMV in the field. We ran it here, and you can see how far that meter is shifted. Now what happens when you erode or corrode material, the meter gets thinner, the tube gets less stiff, and that's why you see those red and blue traces. One is the inlet, the other is the outlet. That's why you see that stiffness decrease. We got the meter back here at the factory, we cut the case off, and then we started using an ultrasonic thickness gauge, and there was up to 7% tube wall loss at the first elbow on one of the tubes. So didn't exactly correlate with the shift in accuracy. The density had shifted about 25% based on water density. The flow error was about 10% high. So flow will go high, density will usually go low, is what happens when you have material loss. This next one is a case on LACT units that were actually built in the Denver, Colorado area, and somehow these meters got overpressured during the factory acceptance test. What happens with freeze damage or overpressure is the tube tends to get stiffer. So you'll see those inlet and outlet traces on the graph, you'll see those shift up. That'll make the flow reading read low typically. So these meters registered in the calibration lab at about 4% low with a big stiffness change. So that was very easy to see that kind of gross damage.
All right. So bringing this all back together, and then I think we'll take some questions. Like we talked about, Coriolis meters are multivariable devices that can be very stable over a long period of time, but we live in an imperfect world, and these sorts of challenges can impact different sorts of people. We talked about how there's a variety of reasons to verify our instruments, and that's why diagnostics that can evaluate complete measurement performance are so important. Not just stopping at calibration, but evaluating electronics and any changes to zero in configuration. And like we said, looking beyond the meter to understand how process conditions can lead to overall measurement performance. Hope you got some value today out of how the power of these enhanced diagnostics can help you achieve measurement confidence. And I think with that, we'll go ahead and take some questions.
Thank you, Taylor and Tom, for a great presentation. Now let's go to our attendees' questions. The first question is the SMV report time-stamped?
Great question, and we get that question quite a bit. That's pretty important for those third parties, especially when they're evaluating and taking this report in lieu of calibrations and proof tests. The answer is yes. It is time-stamped with a real-time clock, a date and time. So yes, that is time-stamped, and the report is a PDF, so it's not able to be edited.
Thanks, Taylor. What monitoring and diagnostics are available outside of ProLink? We use Modbus RS485 and watch a few registers for RAM, EEPROM, etc.
Great question, especially when we're talking about how can these diagnostics scale with host systems. All the diagnostics that we discussed today are available through Modbus 485. Diagnostics are also available through other protocols, HART, wireless HART, for example. We can also map these to discrete outputs. So the answer is yes, they can be mapped to Modbus 485.
All right, next question. Can we use the SMV results for safety system proof tests?
You sure can. Much like partial stroking of a valve, SMV enables you to greatly extend the proof test interval that would require a wet calibration. Our FMEDA scores are all online, or we can email them to you. Typically with a Coriolis system from Micromotion, the safe failure fraction is in the 93 to 97% range to start with. So the standard diagnostics really sees most things that are going on. The remaining items are typically the health of the tube, which is what SMV is best at looking at. SMV, along with a 4 to 20 milliamp feedback loop, checking the zero and checking the RTD, has about a 91% dangerous undetected coverage, and we're used a lot in SIS systems.
Can we install the SMV on the existing Coriolis meter?
Yeah, great question, especially as you look at a large install base and wanting to upgrade meters. Yes, there is a large amount of the Coriolis meters that are out there today that can be upgraded with the smart meter verification software. It's simply a software upgrade process. So the answer is yes, Coriolis meters that are in the field, existing and installed, can be upgraded with smart meter verification.
Are all the Coriolis meters calibrated at factory? Is a calibration report provided?
Yes, they sure are. We have a number of flow labs around the world. They are all accredited and traceable to ISO 17025. That's a NIST designation, and we're audited by an agency called NavLab. A report is sent with each meter, and we also maintain records here at the factory.
Okay, great. How do changing viscosity, pressure, and temperature affect SMV?
That's a great question. And the short answer is it depends, right? It depends on how, especially that stiffness measurement, how is that measured? Going back to, give me just a second, we'll go back to that graph that we're talking about here with the frequency response function, right? It depends how we're measuring this. Because we have 3 of those unknowns, we need at least 3 equations or 3 data points to be sure about the stiffness. There are some methods of stiffness measurement out there that use 2 test frequencies, and that just requires an assumption about constant dampening to be made. Because changes in viscosity can affect this dampening parameter, the 2-tone method can be susceptible to some false results when there's changes in viscosity. But when you're using this 5-tone method that's actually over-defined, it gives us a really good picture and confidence on the stiffness measurement. We account for those changes in viscosity and dampening. And this is actually proven out, as Tom talked about briefly, with the NMI third-party testing, where we tested at varying viscosities and didn't notice any issues with the SMV stiffness test. That's a great question, so thank you.
Next question. Change in stiffness leads to recalibration. What is the tolerance?
In very controlled studies, Taylor showed a graph. Can you flip back to the chemical corrosion? If the damage is very, very uniform, it's pretty much 1 for 1. However, damage rarely occurs that way. The new version of SMV that we just released has a very sophisticated set of statistics where we're looking at flow noise, signal sensitivity, essentially. So it's not a real simple question to answer, but we play with what we're calling a deadband in there as a function of flow noise. If the flow is reasonably quiet, if SMV trips, you're out of spec. But within the band, it's difficult to predict how much the accuracy might have shifted. Coriolis generally, there are exceptions to that, but Coriolis generally is very, very stable over very long periods of time. We've gotten 20-year-old meters back here at the factory for a routine check, and the calibration factor was pretty much identical to when the meter was first made. So our expectation normally is that the meter's not going to shift.
Thanks, Tom. Does the meter require refactory calibration if the meter's core processor has to be replaced for the SMV to be used?
No, it does not. The flow calibration and density calibration factors will remain unchanged. The SMV baseline is a function of some variation in the core processor. It's a fairly simple thing for a service technician to do, but the SMV baseline would have to be reestablished.
All right, we've got a couple more questions here. The next one is, should a Coriolis meter be blanketed and heat traced?
If you're operating at extremes of temperature away from ambient, I'm thinking cryogenic gases or very hot refinery feed, it can improve the accuracy of the measurement. We have an RTD inside the meter that's trying to measure tube wall temperature, and that's for Young's modulus. That determines how stiff the tube is, and we make some compensations on tube stiffness based on that. So if you've got extremes of temperature or a fluid that either wants to solidify or flash, it can make good sense to heat trace or insulate the meter.
Okay, great. Qmax is used to determine mass flow cutoffs. If false flows show up in cold weather in NG, how high can this cutoff be set and still measure low flows accurately?
I think in the interest of answering that more thoroughly, this is from TransCanada, I believe. Brenson, if we could take that one offline, that probably requires a little longer discussion.
Okay, great. We'll do that, and we'll send that response out. All right, last question. Why do we need a temperature when measuring a mass flow rate?
You generally don't check the RTD, but AGA and also SIS looks at it a little more broadly than maybe some metrologists. Young's modulus describes the stiffness of the flow tube, and that drives a temperature compensation in our flow and density calibration factors. The effect on flow is typically for every 100 degrees C change away from zeroing temperature, you have about a 5% shift. So it's a fairly small effect, and some of the agencies want you to verify that RTD is still reading accurately, just as an overall part of the system accuracy.
Thank you. And thanks to our presenters for a great webinar, and to all of our attendees for taking the time to be with us today. Following the webinar, you will receive an email with a link to watch the webinar again on demand. We will post any questions we did not get to today on our website at flowcontrolnetwork.com. Have a great day.